approximating area under a curve. So this is our first step into looking at using integrals, or the definite integral. And so we start out with kind of this basic idea. And although this formula does look a little bit intimidating, I'm going to show how it's used to find the area under a curve, and then we're going to start to attach some calculus to it. Okay. So the big idea here is I've got these three pictures here, and the line going across is the function x plus 4, and we can see it's going from -2 to 2 is the area I'm talking about. So I'm really kind of talking about just this space right in here. And you'll notice I have three graphics here. And these three graphics are kind of distinguished by the way in which they stop at the line. So you'll notice that this one is the left corner of the rectangle. This is the right corner of the rectangle. And you'll notice that this one has the midpoints. And I'll talk about that one towards the end. Now the idea here is a theory based on Archimedes' what is it called? Exhaustion. So he pretty much theory of exhaustion, which he tried to just plug in as many shapes as he possibly could in order to find the area under a curve. Now you can see that these are not curves; these are lines, and I'm using lines just to justify my answer. But we could easily just take take the area of this little rectangle right here, and then add the area of this triangle right here. But showing this idea will help us kind of a little bit better understand at this little less level. Okay, so we have area equals base times height. That's the basic formula that we can use to find the area of a rectangle. So you'll notice if I took the base, which is 1, times the height, which is 5, that would be an area of 5. And you can count the squares to justify that answer. So what I'm going to do here is, in this particular case, I have 4 rectangles. Now I could find the area of these rectangles, add them up, and I'd be just fine. I could even count them if I wanted to. But I'm going to bring in this formula right here. This is summation notation, and kind of break this idea down. So this means the sum. This is the shorthand version of saying we're going to add a whole bunch of numbers together. And so this is the summation notation. And what the top number is the n, and that, as I identified here, is the number of rectangles. The I equals 1 emphasizes the idea of your first point. In this case, we're going to start with -2, or the left bound corner here. And then it's going to talk about the base. Now you'll see that the base is simply 1. And no matter if I put 10 rectangles in here, we would just take 4 divided by 10, which would tell us what the underneath part would be. But this is going to remain constant throughout the whole problem. All right, so let's kind of write this out. So I've started the process here. I've got 4 rectangles. I'm going to find the area of this. All right, and so I'm going to start to write this out. So the first thing is to understand is that all this is saying is I'm going to plug in the left bound here. So you see it's -2. So I'm just going to plug -2 into the function. And as we just talked about, the base is going to be 1. So the base of this is simply 1. All right. And then, of course, we're going to put plus here because we are talking about summation or adding. All right. So we got f of -2. Then we got f of -1 times 1 again because the base is 1. And then again, I'll put the plus signs in red just so you can identify with that. Then we have f of 0. Okay, that's another one of my rectangles. Again, these are just the heights, and we'll see here in just a second what I'm talking about. And then we got plus f of f of 1 times 1. And that's where I'm going to stop right there because you'll notice that I've covered this rectangle right here, and we're talking about the left side. So that's where I get these numbers. Now, you can see if I plug in -2 into this function, that's just going to give me the value of y. So let's see, -2 plus 4 is 2. So we got 2 times 1. And then we got plus f of -1, which would be, you can look at the graph, would be 3, but I can also plug it into the function, so I get 3 times 1. And then I'm just going to put a plus to save a little bit of time. 0 would be 4. 4 times 1, which would be 4. And then plus f of 1, which would be 5 times 1. So if I add all those up, again, we're just using summation notation here to shorthand this idea of adding up all these rectangles. We would get 2 plus 3 plus 4 plus 5, or equal to 9, 12, 14. All right? Now, you could count all these squares and it'll be 14. So again, I just want to overemphasize the idea that we are just talking about a line here, and I'll show what you do in the case with a curve. All right? So we have this general idea here. Now you can do the same thing with this one. You'll notice that this one will come out to 18 if you did the same idea. And I'll just count these really fast. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 is the area. But we know that the 14 is a little short, 18 is a little large. We can see that the blue goes over the line here, so we're kind of a little bit over the area underneath this thing. And then we have the midpoints, and you can see that we have these little bit of pieces right here that could fall into those spots. All right, now the midpoint's nice because it does work with the lines. So our actual, if we figured out the area, it comes out to be 16, which is the average of the two, the smaller area found and the larger area found. The average of those would equal 16. All right, now this becomes the case when we're talking specifically about straight lines. It might be a little bit different when we're talking about the curve, but you'll get a general idea of how this works here in just a little bit. So now let's talk about the idea, well, 4 rectangles doesn't really give me a good look. Like let's say, for example, I want to find, what if I put, and I have the graphic right here, so here's a graphic we're talking about. So I just did, let me zoom out a little bit. This is the same graphic we just had. We're talking from -2 to 2. I put the four things in there. It's a little bit different because of the skewness of the y-axis, but trust me that we're on the same, we got the same formula here of x plus 4. All right, so now let's say, for example, that instead of, I want to be a little bit more exact if I'm using in this case. So let's say, for example, I want to put, let's say, I want to put, let's say 50, or let's say, try something nice here, let's say 20. I want to put in 20 rectangles in this space, all right? Obviously, the width would have to change to 4 divided by 20 because I want to put 20 squares in there. Now, you'll notice when I put in 20 rectangles, I could go through the same process I just did, but in this case, I get a little bit smaller differential, okay? What if I put in 100 rectangles? And I change this to 4 over, and the reason I'm using 4 is because the space from -2 to 2 is 4. And let's say I did this. You'll notice that I've now put in 100 little rectangles. And I could do the summation notation and spend all my time trying to get all these points. You'll notice I'd have to get the value right here, so I'd have to be pretty exact. But again, as you notice that as I put more and more rectangles into this graph, kind of zoom in here, that I'm more and more exact into the function, okay? This becomes really important when we start talking about examples of like x squared. I don't know why my computer's running a little slow here. Let's see if I can refresh it. All right, so let's say, for example, I have the function x squared, okay? And I'm gonna still go from, let's say, 0 to 4, okay? Now you'll notice that if I try to put in, let's say, 2 triangles, 2, and we're going to put in, or 2 rectangles, and we're putting in there. Now you'll notice the space is kind of limited there, right? So let's put in 4 rectangles, and let's make it all a width of 1. So you'll notice here, and I'm kind of going a little bit further into this, is that this doesn't work so well with a curved line, which is why calculus was created, because we don't have necessarily a formula in geometry that says for this specific x squared function, what's the area underneath this curve, or what's the area of this shaded area. You're not going to be able to find it. So what we're going to do is we're going to put in multiple different, or multiple rectangles. So like, let's say, for example, I'm going to put in 500 rectangles. And obviously my width would have to be, because I got 4 divided by 500. And you'll notice that I've put in 500 rectangles, but you'll still notice that there's a little space left over. Even though I'm using the best possibly I can, if I use the right, you'll notice that I'd be a little bit over. Okay, now again, we're talking 500 rectangles here. That's a lot of rectangles, and I'm trying to fill this space up. So what that leads us to, and a long video here explaining this, is the idea that I'm going to put in infinitely many rectangles. Infinitely many rectangles. As n approaches infinity. And that is going to give us what the definite integral is. And I'm going to talk about this in more videos here. So if I'm talking from a to b, f of x dx. Okay, so please understand what we're trying to accomplish here is the idea that the definite integral has this backing it behind it, in that we are putting infinitely many rectangles inside the area, and we're trying to find the we are going to try to find the area of adding up all of those rectangles. Okay, so please watch a couple more videos. I got more coming about this, but we're going to kind of dive into the definite integral here and we're going to find some areas or the value of the definite integral.